Hey, everybody. Welcome back to Adventures in Machine Learning. I'm one of your two hosts, Ben Wilson.
And Michael Burke. How's it going?
And today we're going to be talking about a white paper that Michael read a while ago. And we're going to talk about cows in fields and deserts.
The most exciting topic out of all of the topics.
Hey folks, this is Charles Max Wood from Top End Devs, and lately I've been working on actually building out Top End Devs. If you're interested, you can go to topenddevs.com/podcast, and you can actually hear a little bit more about my story about why I'm doing what I'm doing with Top End Devs, why I changed it from devchat.tv to Top End Devs. But what I really want to get into is that I have decided that I'm going to build the platform that I always wished I had with devchat.tv. And I renamed it to Top End Devs because I want to give you the resources that are going to help you to build the career that you want, right? So whether you want to be an influencer in tech, whether you want to go and just max out your salary and then go live a lifestyle with your family, your friends, or just traveling the world or whatever, I want to give you the resources that are going to help you do that. We're going to have career and leadership resources in there, and we're going to be giving you content on a regular basis to help you level up and max out your career. So go check it out at topenddevs.com. If you sign up before my birthday, that's December 14th. If you sign up before my birthday, you can get 50% off the lifetime of your subscription. Once again, that's topenddevs.com.
Cool. So I'll set up the problem statement and quickly discuss the method, and then we'll get into the philosophy behind it, as well as the nitty-gritty of the algorithms and the solvers. So this paper was developed, or this method, I guess, was developed, I think in 2019 or 2020 by Facebook's AI research team. And it's really cool. And the basis of it is they're looking to develop a causal learning algorithm that is better than all the other ones. So other standard causal learning algorithms are use DAGs or try to just get creative with the data, essentially. And this model does the latter. And what it does is it creates environments and it looks to develop causal inference based on those environments. So what does that mean? Let's take a little bit of a deeper dive. So like Ben said, they use the example of cows and camels, and both have 4 legs and are animals. But the thing is, one thing that is specific to cows is they often have a green background. So pasture, grass, whatever it is. And then camels, on the other hand, often have a sandy background. And so this is a classic example of a machine learning algorithm without any adjustments would train on the background color. And that's actually what happened. I forget the exact numbers, but they trained a bunch of images and developed a classifier. And it turns out that when they changed the background color for a cow or a camel, it just predicted the opposite label. So as you can see, this is a problem for generalization. And instead, what we're looking to do is develop a causal framework that says, well, if basically it uses counterfactual logic, and we'll get into that in just a sec. Good so far, Ben?
Yeah, it's a good overview of the intro and like what they're trying to do. And I think anybody who's listening in who's ever tried to build a CNN classifier, regardless of how sophisticated they're going, will run into the same thing. I have in the past, where you have images from the real world and people have looked at and said, okay, I know what's in this image. I'm labeling it as X. This other one is labeled as Y. And when you train the model, it's going to learn things that's dependent on what it sees in the data. And whatever the simplest path is to differentiate between things, it's going to learn that pattern.
Yeah, that's a really good point. Algorithms they're optimized to take the simplest path. So if there's some correlation or some feature that in this case, in this sample of the data set is really powerful, then that feature will be very important. And when you exit that data space, well, the model won't generalize at all. So basically what the method looks to do is it looks to develop environments based on the sampling schema. So in the example of cows and camels, one could think about the country that they're sampled in, and that might be indicative of the background. One could also think of the time of day or just other pieces of information about how the data are collected. And then what you look to do is leverage a counterfactual framework And so let's get into that in just a sec. For those of you that don't know, a counterfactual is essentially a data trend that we observe that we would have observed without a treatment. So you can think of it as the control group in an A/B test. If we see a data trend and I don't know, we change the button from red to green, well, that's the treatment. But in the control group, we want to see what the data would look like with a blue button. And so with that framework, we can look at average treatment effects and differences between those two groups, and then use that to develop a causal framework. And they sort of borrow the same idea, but what they do is instead of we create, let's say, 10 environments. Each of those are 10 environments from different countries. So Tanzania, Ireland, the sandiest and the least sandy places. So from that, what they do is they look to develop rules. And if anytime those rules are broken, then the model is penalized heavily. So you can sort of think of it like a regularization term that's added into the loss function. And that's actually what they exactly develop is they look to find instances where a rule is broken and therefore that rule cannot be true. So if a cow ever appears in a sandy background, then sandy background cannot create camel or it cannot cause camel. And vice versa, if a camel appears in a grassy background cannot cause cow. And that's sort of how humans think. If there's ever a rule broken, then causality is broken. So instead of optimizing for correlation, we optimize for causality. And that's basically the high level framework.
And it has this very interesting effect when they implemented this in PyTorch and ran it through some of the tests that they did, where it showed something that most people who are familiar with training supervised learning, this is worse. Like their training loss metric went down compared to a traditional optimization technique. I think in the paper, it was like with their colored MNIST data, it's like 76 or 74% accuracy on training. And then when they took that onto test, it was like 10% accurate, which is pretty bad. And then with their approach, their training was in the 60s on both training and test, or on the holdout validation. So this approach of making those restrictions within those environments and saying this penalization term is so strong that I'm going to de-weight this cycle of optimization to say this is not correlated because it's not causal based on that inference that's going on.
Yeah, and that's a really good point. The purpose of most predictive models is to generalize past the data set. I think that's pretty agreed upon. And if your data are not perfectly representative of future data, then you might have issues. And even if it is, you might have features in there that for whatever reason are very indicative of the Y value, but in the real world are not. And so by ensuring that you're learning causal relationships instead of spurious correlations, for example, you generalize a lot better. But as Ben said, that can kill your training accuracy because you're not picking up on random features.
Yeah, definitely. And you can see this with even open source data sets that are very simple, where you're trying to predict, something relatively simple, like, I want to do bike rentals in San Francisco. I want to use that data set. And you might throw in some data in there to say, well, I want month of year in there, and I want adjacency to a holiday, and I want cloud cover percentage. It's going to pick up on whatever that strongest correlation might be. And maybe it's precipitation. People don't rent bikes when it's raining out because that's a terrible experience. But if in data, particularly in the typically spurious assumption that a lot of people have in test being IID. So it's very challenging to get that, particularly if you don't have a truly ludicrous amount of data to train and validate on. If you're not very careful with that split that you're doing and making sure that these two samples are of the same distribution and are independent of one another, you're going to get some really weird results. It's going to learn on something that you didn't want it to learn on. And this happens all the time. So that this paper and what we're talking about is a means of simplifying the process that you would otherwise have to do with building a causal model. I don't know if you've ever had to build one of those, but they're in the extreme to build just due to the amount of time and effort and computation that you have to do.
Yeah, I have. I remember one of the first projects that I was working on was a modeling project, and I talked to our resident expert in causal inference and causal modeling. I was like, which is harder, predictive modeling or causal modeling? And he was like, that's a dumb question. Causal modeling is predictive modeling tends to be more towards optimization, and causal modeling, this was his argument, you have to actually know what's going on under the hood and make sure everything makes sense and then explain it. Predictive modeling can be a black box, and if accuracy is 95%, we're happy.
Mm-hmm.
And it's interesting to see these two fields merge, because black boxes are becoming, at least over the last several years, black boxes have become less acceptable, both from a model trust standpoint. So for stakeholders don't trust it as much. And then also from a generalizability standpoint, we tend to, like, you can backtest obviously, but we want to know that future predictions will be not that bad. So having causal knowledge of what's going on is really effective.
Yeah, and having that causal relationship with rejecting potential features, whether we're talking about images or just data, with new changes in data that are coming in for prediction, this recording and measuring of the real world in order to generate predictions, the model would be aware of that penalization effect of spurious. So if you have a happens, which
newsflash, like every model is going to experience that.
There's going to be some foundational shift in your feature data at some point. When that happens, this approach can actually counteract that to a large degree, provided that it's the training data.
Exactly. And Ben started to get into one of the more technical pieces. And I think we've sort of painted a high level picture so we can start descending into the weeds. But he started talking about the assumptions of modeling. And standard modeling, basically, if you think of most machine learning training scenarios, it's called, this method is called invariant risk minimization, and standard machine learning is called empirical risk minimization. And basically, you can think of risk as sort of like a loss function, and empirical means that it's the data that we observe. Invariant refers to the causal framework, so that it must invariantly minimize risk. And for empirical risk minimization, there are three core assumptions that the paper cites. The first is that data are IID, so independent and identically distributed. And as Ben said, especially within a train test split, that's often not the case. And then if you can just think about it, when you sample from different environments and then you treat those environments as IID, that's invalid. So with test splits and then just other training, if we just look at training accuracy itself, that assumption is often invalid, and that leads to problems. The second assumption is that as we gather more data, the ratio between our sample size and the number of significant features should decrease. So as Ben was saying, if we have a bunch of random features that have very spurious correlations, then this assumption might not be true. But if we're truly learning causal relationships, then as we gather more high quality data, more correct data, those causal relationships should become more apparent and more clear. And then the final assumption sort of is we have to assume is that we have a model that can explain the relationship between our features and if you can't do that, then that's a problem. But often we just have to assume that. So what the paper basically said is 1 and 2 are not valid, and then 3 we just assume because we have to.
Yeah, and that assumption, particularly, I mean, the first assumption is, as they cited in the second half of the paper in their coffee shop transcription, which is really amusing, the big lie of ML is IID. And that holds true, just as you said, with the train test split, but I think it holds even more true when we're talking about utilizing an ML model on data it's never been seen. So when we're doing daily scheduled predictions, there's no guarantee unless you're looking at a fixed closed system that you find everything about it, and then you've really pared down your feature set to things that are observable. You're looking at machinery operating, and you're measuring the vibration analysis and the RPM, and it's fixed set of parameters. Look at the entire environment of all the latent factors that are associated with that. So even in those cases, you're still not guaranteed IID over time, even though we all say that, yeah, it is.
we're taking
a sample from the population of training at this time. That's what we're using. And then when we're predicting in real time or in batch over the next n number of weeks and months and years, it's going to be the same distribution. Well, generally not. Things change. Entropy happens and things fall apart. And that's true of pretty much any model. Your third point, the assumption that actually it's prediction.
Yeah, those are really good points. You sort of hinted at one thing that I wanted to highlight, which is causal learning isn't always the best option, maybe. Could you give some examples of data generating environments where straight up optimization might be the best option?
Oh, that's a good one.
And I think you hinted at it. It's a knowledge of the data generation mechanism and knowledge of future data generating mechanisms. So if it's a physics-based system or a machine, we might be able to assume that prior data will look exactly like future data. But in most product applications and most big tech applications, that might not be the case. So I was wondering if you had any ideas on that.
Yeah, definitely. I was just trying to think of some of the use cases I've been involved with over the last couple of years. They're very few and far between where we can say, hey, for training and everything that we're predicting on, and we can validate this, as you said, through back testing. We look at random samples of the data over a period of years, and we see, yeah, there are some variations, but the variance within each of the features being collected it follows like over extremely long periods of time because we're tightly controlling the data that we're collecting. It's sensor data. It's measuring Newtonian properties of things. So in the respective use cases like that, where we're measuring equipment, we're measuring physical properties of something, that data being collected is bound by an environment law, which they kind of get to in the paper as well when we're talking about environment. If we're constraining what we're measuring and what we're predicting within the boundaries, you have fixed limits on when you're measuring physical systems. If we're talking about predicting whether a rotating piece of machinery is going to fail, we know that we're not able to measure below 0 Kelvin, or we're not going to have a temperature value that is going to be hotter than the core of the sun. So you have these constraints, and you know over time that you're going to be in this range of what is the temperature of this piece of equipment at this place on Earth, because there's a melting point to any piece of equipment. And then that environment constrains itself to the point where you can say, yeah, I have ID, because in training, test, holdout, and prediction data sets, but an infinitesimally small subset of ML application that I've seen. And a lot of those aren't even handled with supervised learning. They're handled with physics models. You know that relationship. You already have that causal understanding. So you just programmatically write that and say, hey, if I have these conditions, this is a problem. Otherwise, continue not sending me alarms about something. Supervised learning isn't used for because it can be easier to implement than writing a physics model. And it can also allow you to do a lot of them in parallel without having to write a bunch of custom code for monitoring systems. What you alluded to, production use cases in industry that people are applying machine learning to, a lot of them have to deal with humans. Like, how is this person going to interact with my company's products? Or what is going on with this geopolitical? What is the risk of this thing? And is this person trying to do something to attack my company? All of these sorts of things have so many latent variables that you can't collect. So isolating the data that you are collecting to getting a causal relationship is the big gain that this paper talks about.
Yeah, exactly. And I think you made a really interesting point in that most physics-based models use physics models, which makes a lot of sense. And for that to work, first of all, that's the goal of modeling, is to predict the future, right? And if you have a really good understanding of the system, then you probably don't need machine modeling or machine learning, like Ben hinted at. And in that case, you can just develop some mathematical model that creates the relationship between X and Y. But for machine learning, we're looking to develop an estimate of that relationship. And so causal learning, basically, if you can't write out a mathematical relationship between X and Y, causal learning is probably a really good option for you. If you don't have perfect understanding of the data generating mechanisms, then causal learning can improve any generalization to new data sets. So that was basically the gist.
Yeah, I couldn't agree more.
Hi, this is Charles Max Wood from Top End Devs, and lately I've been coaching some people on starting some podcasts and in some cases just taking their career to the next level. You know, whether you're beginner going to intermediate going to advanced, whether you're trying to get noticed in the community or go freelance, I've been helping these folks figure out how to get in front of people, how to build relationships, and how to build their careers and max out and just go to the next level. So if you're interested in talking to me and having me help you go to the next level, go to topenddevs.com/coaching. I will give you a 1-hour free session where we can figure out what you're trying to do, where you're trying to go, and figure out what the next steps are. And then from there, we can figure out how to get you to the place you want to go. So once again, that's topenddevs.com/coaching.
And as you mentioned earlier, when you asked your colleague before of like, hey, which one's more challenging? I kind of chuckled at that because causal learning, when you're building those sorts of models, you need to understand the problem space. You don't need to understand it. That's the point of the modeling, is to say, hey, what actually impacts what? But you have to understand the problem space to such a degree that you can actually build the relationships that you're going to be testing with empirical data. And that involves creating DAGs of saying, if this changes, then it changes this, and this has a relationship here, and these don't have a relationship. And you have to design all of that and then run a bunch of experiments and saying, hey, start varying things for me and selecting vectors of data and tell me what the relationship is. It's very complex. It requires domain expertise. Whereas, as we've been saying, traditional ML, you don't need to have all of that. It helps if you do. And it's really beneficial if you work with somebody who really understands. In fact, you should be doing that, but you don't have to understand it to the degree that you would for causal modeling.
Completely agree. And even with causal modeling, there's another layer of whether you need statistical significance of the causal relationships. That's often pretty easy to add in, but just another note there. And then I also wanted to quickly, before we redescend into the weeds and talk about optimizations, and I just wanted to touch on the philosophy behind this because I think it's super, super interesting. And I don't know, there's something interesting about it. So a long time ago, people studied the brain and said, hey, we have neurons. That's a cool framework. And then in the 80s or 90s or whenever it was, neural networks were proposed as a method for solving problems with computers, essentially. But back then, we didn't have the infrastructure, the computing power, or anything like that. And so we were unable to run large-scale neural networks. But with the rise of computing, we started using neural networks for basic things, and we were able to sort of approximate the brain. Causation is not a real thing. You can't go touch causation. You can't go grab causation. You can't look at causation. Causation is a construct by the human brain, and it's made through the relationship with neurons. And so what we're looking to do is take neural networks a step further, and just black boxes in general, but take them a step further and make them more like the human brain. And essentially what we're looking to do is approximate what humans do as a child. So a child sees a pan on the stove and is like, I'm going to touch that. They get burnt and they say, oh, things that are on the stove are hot. Well, a year later, they come back and they touch the stove, but the stove is off. Well, the stove can't be the cause of burning my finger. Maybe there's some other relationship. So they go out and test different things. And what essentially this paper is looking to do is build in that trial and error learning framework into the loss function. And what they do is they create test environments of different scenarios of touching the pan when the stove is on, touching the pan when the stove is off. And they ensure that the same cause occurs in each environment. If it doesn't, well, then it can't be a cause. It might be a strong predictor or a strong correlation, but it can't be a cause. So I just thought that was freaking awesome. And it's cool to see how algorithms are starting to become more like humans and borrow the best parts of humans. So we'll see. We'll see how that goes.
That's an awesome analogy, actually, with traditional ML that we're looking at for that use case of touching the stove and getting burned by a hot pan. A traditional supervised learning, if it doesn't have all of those combinations of when was the last time something was cooked in that pan on the stove, what is the state of the knob for the burner of that stove, what type of pan is it? There's a lot of data that you could collect about that. But if you don't have all of those permutations and you don't have enough samples testing, like, hey, is it hot? Yes or no? Based on this data of the state at that moment, you run the risk of it doing what the child did at phase 1, is just saying pan on stove, hot, burn, yes. It sees that the pan is on the stove versus the pan is in the cupboard, saying it's burning hot, even though in reality, we know from our experience and our brains can understand, and we can, put our hand above the stove and say, do I feel heat coming off of this? So the model, if you're not careful with your training data, is going to learn a spurious correlation that you don't really want it to learn.
Yeah, exactly.
That's where we all are. And as data science practitioners, that's where we all are. Whenever we're building a model, we're fighting against that.
Yeah. And just think about what would happen if you got all of your data about the stove from the kitchen in your house versus a kitchen in a restaurant versus a kitchen in a restaurant that is at peak hours between 7 and 9 p.m. It's like the data generation is so important. And again, what this framework looks to do is overcome crappy data generation mechanisms or biased sampling, because you can't have perfectly unbiased sampling almost ever.
Yeah, there's too many. We just came up with a handful of them, and there's an infinite number of latent variables that could affect that. We could spend the next several hours just whiteboarding a bunch of ideas of like, what other data could we collect that could explain whether a pan is too hot to touch or not? And that's the reflection of the reality of any project that you work on, is you're never going to collect all the data. It's impossible. You're never going to have true causal understanding of a problem due to the fact that you can't collect the empirical evidence to explain a causal relationship that would be able to be accurately represented in traditional machine learning. So this approach of saying, I'm going to sample things and I'm going to say, holding this one element constant and I change these other things, what does that actually do to the prediction, my optimization that I'm doing? And how does that impact how I should de-weight this one particular feature? And it's a brilliant approach. Reading through the paper times this week after you sent it to me, I was like, this is so cool. And it's actually not too dissimilar from how ML explainability algorithms work. So like the SHAP algorithm is using a somewhat similar technique where we're holding certain indexes in our feature vector invariant and synthetically varying other features to determine what is the actual importance of these factors. How much do they impact this trained model and what it's actually predicting, and saying, oh, this is the directional magnitude of this one feature. This is how it actually impacts. This paper that we're talking about is sort of taking that idea and saying, let's just put that into the training process. Hold elements, hold vector indexes invariant, change other things around it based on our sampling, and say, do we detect conditions where if we change this one thing, the prediction is completely wrong? And those really big switches dramatically impacting the prediction, those need to be weighted very differently than the ones that are just, oh, there's maybe a weak correlation here. Yeah, I have a positive correlation, but it's the ones that, hey, if I just switch this one thing, it completely nullifies this prediction. That's the big improvement here. My curiosity, and we talked about it before we started recording today, is like, what is the computational complexity of doing this, where we have to build these environments and these synthetic elements, whether it be a convolution over a matrix or we're doing vector processing. This is a lot more iterations that we would have to do in order to determine that relationship. So it'll be really interesting if this does take off. What is the value to people in industry comparing these two things? Because it's going to be added cost, but there's going to be added accuracy. So I'm curious to see where people's cost benefit analysis will fall out on this.
Yeah, it's a good. I have no idea. And just another note on industry adapting to this method. This paper only covers classification, and they're working on regression topics, but that was left for future work because it's apparently a lot more challenging from a mathematical standpoint. And I could see why. But yeah, right now, at least as of the date that this paper was written, they only have it for classification. So
I imagine this would be non-trivial to do for a continuous predictor, because you would have to estimate the magnitude change and how much is that deviation, and you'd have to run a whole lot more iterations in order to determine that. It's like that in the SHAP packages. That's the difference between like your tree solver versus the tree solver. If you're running with a tree-based algorithm, that thing executes pretty quickly, even on a relatively enormous data set. And then if you can't support that and you have a model type that isn't tree-based, you have to use like a kernel solver, or there's also linear solvers, but they're restricted. But that kernel solver is brute force. It is, I have this black box that I'm throwing a vector of information at, and it's going to provide a prediction, and I'm just going to mutate a bunch of stuff and throw it at that and see what the differences are, what is between these. And it takes a long time to run, like a very long time to run. It's on the order of like 100 to 1,000x longer than it took to train the model in the first place, just to be able to explain it.
Yeah, that makes sense, but goddamn.
It's some pretty beefy hardware. Some of our customers at Databricks who are needing model explainability because of legal requirements, sometimes they don't want to, or they've tried to use certain types of, they're like, yeah, that's cool, we know everybody's using that, but we don't want to use it because it's not a really good fit for our use case. But we need explainability. And then they get down the road of like, all right, we're going to use SHAP. And they're like, wow, why does this take so long? And like, this costs thousands of dollars thing. So, yep, sorry. Like, we're working on it. When we figure it out, you'll be the first to know, but it's computationally intense. So it'll be interesting to see this taking off and eventually packages being written or pre-trained classifiers that Facebook can offer to the world based on these papers saying, hey, here's the way to do this, and here's the algorithm, and we created a structure that supports this, to know if when you need basically A100 GPUs and you need a cluster of them in order to run this, even for relatively simple data.
Yeah, one of the companies so we have weekly speakers. Either someone internally presents an ML paper or we have someone externally come in. And one of the people that came in was a founder of a startup that was trying to just basically sell us his product, unfortunately. But it was all about model explainability. And there's so many new companies that are working on model explainability. Obviously, not all of them will succeed, but it's such a hot topic right now because of A, generalizability, B, trust. Also, with the general AI discussion, everybody's like, you tell an algorithm to make a bunch of paper clips and Terminator happens. Well, if we know what's going on internally, maybe that won't happen. So I think there's a bunch of different reasons for why it's such a hot topic. And Databricks is, I'm sure, going to put out some great products soon, but it is also challenging.
Yeah, challenging, and it's expensive to do it. And that brings me to another meta question. Not Meta the company, Meta the concept. At what point does ML become such a commodity because of the advances and the general acceptance that people have? Like, algorithms such as what we've been talking about get to a point where, hey, they're really good and they're really generalizable and people trust them. We can explain them pretty well. When ML becomes a commodity, anything that becomes a commodity becomes optimized for price. And what is the performance considerations or need to come up when this becomes something that just everybody does?
So the premise is machine learning algorithms become something you can buy at the grocery store, basically. You can like make them really quickly and they work really well.
Maybe not quickly, just
fair. Okay.
They're reliable enough that people trust them, and they're sort of ubiquitous throughout industry. Like, every company has their suite of ML models that are running every single day. And how much is that going to cost the company for things that are just expectations, and what is that load going to be on cloud providers? I see it pretty much every day. There's allocation problems on all of the three major clouds that we have, where somebody's like, hey, in case I want to do modeling, we were doing this one model, but we found that if we split it up based on region and we create 1,800 different models, they're all more accurate than that one meta model. It's like, yeah, sure. You're just removing one. You're creating different ecosystems, these different environments, basically, for each of these models. You're eliminating a bunch of latent factors that are influencing the performance of the one meta model. But then they're like, whoa, we tried to run it asynchronously. We tried to kick off a job that did training all in parallel, but because we got a cloud provider limit. They're like, do we need to go to a new region? I'm like, no, you need to talk to the cloud provider to get more allocation, but what's your budget for this? And they're like, whoa, we didn't know it was going to cost that much. Like, yeah, it's expensive. Yeah. But if everybody's doing stuff like that and everybody is going down that route, how big are data centers going to be? How much silicon are we going to be mining and forming into wafers? It's an interesting thought to consider, where these models become more powerful, more predictive, more reliable, because they don't require a team of 8 statisticians and 4 ML engineers to build a solution that's based on a bunch of statistical analysis to determine spurious correlations before you even start feature engineering work. A model can just say, yeah, you can throw some garbage data in here, relatively garbage data, and we're going to find these spurious correlations and reject them from the model's influential weights. That's what I meant by commodity.
Gosh,
when it becomes easier, then it becomes more expensive.
Hey, folks, if you love this podcast and would like to support the show, or if you wish you could listen without the sponsorship messages, then you're in luck. We're setting up new premium podcast feeds where you can get all of the episodes released after Christmas 2020 without the ads. Signing up will help us pay for editing and production, and you can go sign up at devchat.tv/premium.
Yeah, and even with this method, you could argue that you should throw in more data because it will only find causal relationships, theoretically. So let's throw in ESPN data. Let's throw in Twitter's most recent feed. Well, why not? And so, yeah, that's a really good point, that future cloud computing demand will no doubt increase just due to scaling of industry. But as we have more robust algorithms that can handle really crappy data, there's a lot more automation in the model fitting process. So people would just throw everything at the model and see what it can output. So, yeah, I mean, I don't know.
Arguably, people are already doing that. That was the big promise of XGBoost when it was released. It was like, hey, it'll autonomously reject poor correlations. You can throw whatever you want at it. It's only going to look at the most important features. And it's, yeah, that is true. That's how that algorithm works. However, it's going to optimize for the greatest correlation that it has. And if you throw a bunch of junk into it, it's going to optimize pan on stove means hot. And that's the only thing that's going to look at. All those other features that you throw in there, it just ignores them to such a level that it's really only looking at 1 or 2 features. So that was an issue, and it still continues to be an issue for that algorithm. And then other companies have followed suit. All XGBoost and big tech companies have released their own sort of versions of extreme gradient boosting. So you have LightGBM, you have CatBoost. These algorithms do similar things and trying to solve kind of the same sort of problem in slightly different ways. But people got the wrong message, I think, of like, shouldn't just be throwing garbage into a model and then it'll just magically do some stuff for you. But this paper could theoretically do that. It could say, hey, these things are pretty important. Instead of just saying I'm finding these 2 features that are of greatest correlation, it could be rejecting the things that have extreme correlation with your target and in favor of 30 other features that are actually less correlated, but they have a better chip to that predictor. And you could get away with throwing in just tons of data. Be like, hey, I'm going to throw 1,000 features into this thing and 10 million rows of data. And it probably, on holdout validation, it probably will beat any other approach that's out there.
Yeah, just to be also perfectly clear, this isn't a XGBoost equivalent because there's a lot of design in how we create our environments. And there's lots of subject matter knowledge, and that's a pretty labor intensive process. So in the cows camel example, we first of all knew that background was going to be a meaningful feature and a potentially correlational feature and not causal feature. Second, we knew a ton about what different locations have in terms of their natural landscape. So based on being just everyday people and having subject matter knowledge about different countries and where cows and camels live, we're good to go. But think about more complex examples. I don't know that it will be that easy to develop those environments. And it's tough to come up with an example off the top of my head, but it assumes a lot of A, subject matter knowledge, and then B, it assumes that those environments are very good examples of the sampling schema. So again, we assume it's IID. It's not IID almost ever. But then we have to say, all right, it's not IID. What is the true sampling schema? And that's a really tough question, in my opinion. And personally, that's other than compute power and computational complexity. I think that's one of the biggest issues with this method. So it's not a short-term, quick and easy fix. It's for really complex, really important models where we do know the data generation schema a little bit.
Yeah, I mean, definitely. And you have to not only understand what data is being collected and what, for our image example here about cows, we would have to understand what are the potential latent factors in that environment that we'd have to collect data on to explain the causal relationships. So if we're doing picture generation, instead of just data augmentation that people normally do with CNNs, we're like, oh, I'm going to flip the image. I'm going to invert it. I'm going to mess around with the color space. I'm going to throw grayscale versions of this in there to try to counteract. That's traditionally what you would do with the CNN to get it to generalize better and hope that it doesn't learn the things you don't want it to learn. Like, oh, if it's green, then must be cow in the background. But what happens when you put a cow on a boat? That's an environment that a cow is not normally in. They don't live in the ocean. But what happens if you're transporting a bunch of cows and somebody takes a picture of it? Do you want it to detect cows? And if it was only just looking at the background, what would that classifier do? It would have probability membership being extremely low to anything that it had seen before, and it'd probably get pretty confused. It'll give you a prediction in most frameworks, but it won't be something that you can rely on. But with the correlation and building that environment, saying, okay, I need all of these different picture environments in order to define the ability for it to disambiguate between cow and camel. Do you also superimpose pictures of cows in space on the moon? Like, those are the things, like that's examples. But any supervised learning that we're doing, we should be thinking about that in the applications of an algorithm like this, is understanding that problem space for predicting what a customer's next action is going to be interacting with our product. What are all the different possible avenues? If we're saying probability to churn based on how frequently we're sending push notifications to their phone, well, what are all those latent factors that go into that? And there's a lot. So, yeah, interesting philosophical thought path.
Yes,
for this.
Agreed.
All right, man, this was fun. Good discussion on a really cool paper. Next week, do a pretty fun group of people. It's going to be the open source ML Flow development team, some colleagues of mine, and it'll be a panel discussion. Michael will be grilling all of us on all the questions he wants to know about developing one of the successful open source toolkits that's ever been made. That should be a fun one. So yeah, make sure to prep your questions, man.
Yes, sir. Cool. Yeah,
right, so
was great. And I'll see you next week. And also thank you everyone for tuning in.
Take it easy.
Have a good one.
Bandwidth for this segment is provided by CacheFly, the world's fastest CDN. Deliver your content fast with CacheFly. Visit CACHEFLY.com to learn more.